All right, good morning, everybody. Today we're going to begin looking at the kind of the final major data structure we're going to examine this semester. So I want to begin by doing a bit of review about the different data structures we've looked at, their roles, their properties, and so forth. Think a bit about some of the pros and cons of these various data structures, and then talk about this last important structure we're going to be examining. So, the first major structure we looked at was the array. So, just for review, would anyone care to share what you remember about what's important about arrays? Why do arrays matter? What are they? Yeah, great.
It's a list where all of the entries have a single index or have a given index.
Yep, every entry has an index. Good. And the fact that every entry has an index is very, very important. But what's crucial is the fact that these indexes enable fast access to elements of the array. So given an array and given an index, the time necessary to retrieve the value at that index does not depend on the size of the array. So it's fast access, that is, does not depend on array size. Let me know. But of course, in practice, they're all going to have a finite amount of RAM. They tend to have a lot of RAM these days, but it's still a finite amount. An array says, I am reserving this subsequence of RAM. Now, one of the physical properties of RAM is this fast access. That is, in principle, you can think of the main memory of a computer as a single giant array, and each location in that memory is just indexed as if it were a giant array. On a physical hardware level, there is circuitry that basically doesn't care or doesn't depend on where in memory it's going. Regardless of which memory address it's looking at, it takes the same amount of electrons traveling through circuitry to retrieve that data. It's just independent of that on the level of the hardware. For details on this, you can take my computing organization class, which I'm teaching next semester. But that's kind of the hand-wavy, high-level view of the matter. So an array, then, as a view of a section of RAM, is, in a sense, one of the most primitive types of data structure available. Primitive in the sense that there's not very much abstraction between array and RAM. The only real abstraction is the idea that you're limited to a specific area and you index based off of where that area starts. So that is an abstraction, but beyond that, the array is just a view of RAM. So the array is one of the fundamental building blocks of our data structures because it so closely matches the hardware. Another fundamental building block that we've seen in many different forms over and over again is what we might call the idea of a node. That is, we have, and in terms of Java, nodes are typically represented by an object, right? And so the idea of a node is that we allocated some slice of RAM, but unlike an array, that slice of RAM contains heterogeneous data. In other words, within the node, there can be a couple of different kinds of thing. You could have a string coupled with a reference to some other node. And really, that's a distinguishing characteristic here, is it's not just typically an object, but it's an object that has references to other objects anywhere in RAM. So, using arrays and nodes as building blocks, we can make just about any data structure that we want, right? So let's review what some of those are and how we can think of them in terms of being built out of arrays and being built out of nodes. So first, we'll think about the idea of a linked list. And so the idea of a linked list is we've got some kind of sequence of nodes where each node contains data and a reference. So once we've got the idea of a node and the idea of an array and the idea of a linked list, we can think about different forms of the idea of a queue. That is some data structure where we put things in and get things out in some kind of an order. And we looked at essentially three different concepts of this. So the first such concept we looked at was the stack. Then we looked at the queue. And then we looked at the heap, or a priority queue. And all three of these are readily built either using arrays. Well, a heap, you really wouldn't want to use a linked list. All of them can be built with arrays. Stacks and queues can also be built reasonably effectively with linked lists. So next, we thought about taking an array and sorting it. And the beauty of sorting it is it enables fast search. And so in order to do this, we had, of course, to examine sorting, generally speaking, and think about different ways of doing that. Having thought about sorting and searching, a closely related idea to the sorted array is the skip list, which is more of a node-based data structure. But like a sorted array, it keeps everything in order, but the structure itself encodes how it's going to be searched. And so we had our piles of nodes helping take care of that. Thinking about skip lists and the fact that in general they work pretty well, but they aren't necessarily guaranteed to do so, also then got us thinking about the idea of a search tree. And at its most basic level, the idea of a binary search tree, we can think of them as being built as if they were a linked list with two next pointers. In other words, the left and right children. So all of these are just very closely interrelated. They're all just tiny variations of the same kinds of ideas. And then we examine the idea of a trie, which we've been working on this week. So kind of looking back at everything, first of all, I want you to be conscious of the fact that you've had a chance to learn an awful lot this semester. This information is foundational to thinking about computing in general, in the sense that a lot of what computers offer is that they can store lots of data. But if they store lots of data, you have to be able to find it. And not only find it, but find it fast. And not everything is as fast as everything else. And so to that end, we've had discussion about the big O concept, or more formally, asymptotic analysis. And in thinking about asymptotic analysis, we've come to see that there are different kinds of trade-offs between these different data structures. So, for instance, an array, set and get, those are constant time, but insert or add first, those are linear. Add last is kind of happily constant nevertheless. With a linked list, something like a set or get can actually be linear time, especially thinking about a get, but as long as you've already got a reference, insert can be constant time. And so you've got kind of these two extremes, and then a lot of the other data structures we've looked at have tried to moderate these extremes. And an important form of moderating extremes is to use comparisons to cut things in half. So the beauty of the idea of a comparison is you can compare a value against some value in a data structure, and if it's less than that value, you can rule out the big ones, half the contents. If it's greater, you can rule out the other half. And if you iteratively rule out one half every time as you try to get down to one item left, we find that the number of times we apply the 1/2 idea, and so we've seen this before, but I'll review it just for fun, is we have 1/2 to the k equals 1 over n, 2 to the k equals n, and so k equals the log base 2 of n. And so this little factor just kept cropping up all over the place because of the ability to use comparisons to cut things in half. And so we saw this in huge numbers of places. First in the heap, then in merge sort, quick sort, binary search, and then the binary search tree. All of these wound up having some kind of log 2n factor associated with them. Now with the trie, we entered kind of new territory because the trie was the first data structure we looked at where retrieval of a string key did not depend on n. So this is new territory, and there are interesting questions to ask about how does it get to that point? And the way it gets to that point is to recognize that a string is built out of more specific stuff than just anything you can do a comparison on. So the idea of comparison just means that you've got some way to put this data type into what's called a total order. In discrete math class, you talk more about that, but you can see its applicability here. Total order means you can have a well-defined comparison between any two elements, which means you get to do things like sort them and cut them in half and so forth. But a string actually lets us think about quite a bit more than merely comparing. That is, you can think of a string being a sequence of characters. We saw with the trie that we can actually reason in terms of these characters because each slot in the string comes from a limited alphabet. And because it comes from a limited alphabet, we can do operations on each of these characters individually, and then the time complexity in the end really just depends on the length of the string. So with the trie then, what we had to reason about was, first of all, the size of this limited alphabet, which we called B. And that gave the branching factor in the trie. The length of the string winds up corresponding to the depth of the trie. And here's something really interesting about n. So when we think about, given B and D, how much stuff can we actually store in the trie? We realize, well, at each level, right, I can go B different directions. And so, and I can do that up to D times, right? So I've got B times B times B times B, and I can do up to D of these. So interestingly, n will be less than or equal to B to the D power. And this in turn emphasizes the enormous importance of understanding what B and D are to understand how efficient the trie has a potential to become. Now, the trie is a pretty fast data structure for representing a set of strings or a map or dictionary that are keyed by strings. On a practical level, we can kind of do faster most of the time. So as the vaguest imaginable analogy, this is kind of like how merge sort, guaranteed n log n, heap sort, guaranteed n log n, quick sort, when it behaves, it's n log n, and then sometimes it doesn't. What we're about to look at is kind of like that. Its time complexity is basically very similar to the trie, but it's much more array-based. It has fewer cache misses, and so in practice tends to run about 3 times faster. That's just based on my own personal experiments with having implemented both these hash tables we'll be looking at and having implemented a trie. So, Dr. Godrich has another set of cards for you all to play with. So let me pass these out. How many do we have today? We have 6 people. And I have 7 decks. And not quite enough fingers to carry them. So here we go. So you can look at them, you can admire the artwork for a moment, and then I'll be back around with another little set of cards for you all. Okay, this next set of cards is going to be the numbers 0 through 7. Some of these are coming in little plastic envelopes, so just make sure you put them back in there when you're done. So, examine your cards. What you'll see when you examine your cards is that each card has an animal on it, and the animal has a name. And then in the corner there are some numbers. So here's what I'd like you to do is take your number cards out and lay them out in order. So you should have 0 on the left, then 1, then 2, then 3, 4, 5, 6, and 7. Kind of like this. And now what I want you to do is you can mix up your animals a little bit, just shuffle them a little, okay? And then what I'd like you to do is grab one animal at a time and look at the number in the upper left corner. So it's going to be kind of gold highlighted. And place your animal in front of the number that corresponds to. So do that for each of your animals. And if there's more than one that hits, that's okay. Just kind of make a little pile or kind of lay them out like so. So it'll take a couple minutes to get that done. Okay, so look at your pile. Does anyone have any laid out such that every number has only one card? So everyone has at least one, what we're going to call a collision. Okay? Now, do a little survey. What's the largest number of cards anyone has assigned to a specific number? So how many do you have? You have 2. What about you, Graham? 3. What about you, Elijah? 2. Ivy? 2. 2. And Dr. Professor Simi, 2. Okay. I got really unlucky. I've got 2 numbers with 3. I got a bad shuffle. So what you have in front of you is a hash table. So you can look at those numbers 0 through 7. Those are the indexes into an array with 8 elements. Each array can contain some number of items. As you look at it, most of your cells probably contain 0 or 1, and then there might be a couple with 2. If you get really unlucky, there might be 1 or even 2 with 3. So the first question, though, is how do we have come to associate a number with a string? And the answer is that there are an awful lot of ways to do this. The cards you're looking at here, let me go to his little page about this. So Dr. Goodrich is currently putting together some web resources to give rules for playing games with these cards and so forth. So this number comes from using a hash function called murmur3. I'm not going to go over that with you today, but I'm going to begin just by motivating what is a hash function? What does it look like? And once we have a hash function, you just leave your cards in front of you. How does it enable us to build a hash table? So intuitively speaking, just given what you're seeing in front of you, we know that our hash function needs to take a string and produce an integer. So really, any function that takes a string and produces an integer is a valid hash function. Now, just looking at what's in front of you, what are characteristics, do you think, of a hash function that's good as opposed to a hash function that you might consider to be bad? And you can be as extreme as you want as you think about this. You can even think of examples of, say, an obviously bad hash function. What makes things good or bad? What do you think you want? Do you think you want lots of things all in one cell, or you want things really spread out? Spread out. That's right. So Pam, why do we really want things to be spread out? It makes it useful. I agree. How does it being spread out make it useful? Yeah, you're in.
It's because if it's stacked on top of each other, we would need to first find a certain index, and then we need to search upwards from there instead of just finding the index.
That's right. So Ire spelled it out very nicely, and I'll repeat what he said. If you've got a big stack at an index, then when you go to that index, you have to examine every single card in that stack. On the other hand, if you only got one or a small number of items, you just do your array index, and bam, there's your value. But if you've got a whole bunch there, then you have to kind of walk through all of them. So given that extremely important observation that what we're trying to do with a hash table is leverage the high efficiency of an array by using the hash function to spread things out to keep each array cell as compact as possible, what might be an example of a pathologically bad hash function? Something that's so bad that it renders this entire exercise pointless. All the strings go to one cell. Exactly. So an example of a bad hash function is hash of anything equals 0. Now, hash of anything equals 0 takes a string parameter and returns an integer. So it's a valid hash function. But it's really bad. Because what we're trying to do with the hash table is spread things out so that we can leverage the array indexing to quickly find things. So the data structure is still correct in the sense of correctly returning the value you look for, even with this terrible hash function. It is, however, pointless to do that. Kind of an easy way to think about this is you've got an array of linked lists. It's kind of like the inverse of the skip list where you had a linked list of arrays. You've got an array, and each array has a pointer to the first element of a linked list. And the more things that get in there, the more degenerate the hash table gets. And if everything goes to one cell, you've basically recreated the linked list. That's bad. That's bad. Okay, so if that's a bad hash function, we could imagine that the best imaginable hash function somehow takes a string and then assigns indices. And I'm going to abuse some mathematical terminology here. I just want to convey an idea. Assigns indices with roughly equal probability. So in other words, given some arbitrary string coming in, the probability that it hashes to a particular index is roughly uniform. And again, this is mildly abusing the idea of probability a little bit, but I hope it conveys the intuition that I'm going for. So between these, we have actual hash functions. So one way to think about this conversion process from a string to an integer is to think about how a string fundamentally is encoded within the machine. So to think about this, I'm going to jump all the way back up here and point out that strings are, at their core, arrays. Now, within the memory of a computer, all that can ever be stored are binary numbers, ones and zeros. Now, in practice, we don't tend to work with them directly because that would drive us insane. Instead, we set up correspondences between sequences of binary numbers and concrete values that are easy to reason about. Specifically, oops, I'm just flying all over the place here. if you imagine taking, say, 3 binary digits, we would be happy to let 0, 0, 0 be 0, 0, 0, 1 be 1, 0, 1, 0 be 2, 0, 1, 1 to be 3, and so forth. And then 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, and 1, 1, 1 is 7. I maybe did that a little too easily, but the reason that we set up these correspondences is because each of these zeros and ones corresponds to a circuit element that either contains a charge or does not contain a charge. And then you put lots of them together and you can think of them as binary numbers, which you then add up like this. So then coming back to thinking about strings, what we do, and we've talked about this before, but it's well worth reviewing, is we'll put in a little level of indirection here. And what we'll do is set up a table that takes these integers and corresponds them to characters. So for instance, 65 is the letter A, 66 is the letter B, capital, 67 is C, and so forth. And this encoding is known as Unicode. And it's a fairly involved scheme that allows us to encode every character from every human language ever. In order to do this, a single Unicode character can be up to 4 bytes in size, 32 bits. So when we say 32 bits, what we mean is 32 little ones and zeros enable us to uniquely identify each of these characters. And so with 32 bits, you've got 4 billion options, and that turns out to be enough to handle really fun things like Chinese, Egyptian hieroglyphics, and Sumerian cuneiform. So as long as you have a font, that is a correspondence between this number and a little pattern of pixels that looks like it, then you can type in Sumerian all you want. Sumerian is pretty amusing. I went to a museum that had some Sumerian artifacts. And so they had lots and lots of tablets inscribed in cuneiform. I didn't realize quite how tiny cuneiform writing was. In any event, the most bizarre thing I saw was an envelope that was broken off and had a letter inside it in a different color. So the envelope, this clay envelope, was white, had cuneiform writing all outside of it. And then half of it was broken off, and coming out of it then was a cuneiform letter in red clay. So they actually had letters and envelopes in clay. Unreal. Anyway, I'm guessing it was like a secret message, to be opened only by sender. So you can represent all of that in Unicode. So all of this is just a fancy way to say that when we think about the idea of a string is really just an array of ints. That's all it really is, because every letter in the string has an integer representation thanks to Unicode. So that's really interesting and really gives us a way to think about what a hash function ultimately must be doing. A hash function gets a string, which is really just an array of ints, and does some math to combine them. So here's the fun part then. Off the tops of your heads, and this doesn't have to be sophisticated, what might be some math you could do to combine all the ints in an array into a single int? What are some things one could do? You don't have to think real deep about this. If I've got 2 ints and I want to make them into 1 int, what's something I can do to them? What's that? I can add them. Yeah. So if I have 10 ints or 100 ints, and I want to make 1 int out of them, what could I do? I can just add them all, right? And so that gives us an actual hash function, right? So I could define my hash function on a string to basically just be something like this. Total equals 0 for each character in S. Total plus equals the integer that corresponds to the character. And then I can return total. Bam! We have our first real hash function. Yeah, this could work, right? Now, there are two complications that we need to think about. First complication is this. I have a hash table with n elements or n entries. I'm going to change that to entries. Okay. I have a hash table with n entries. Is every possible sum I get from this going to correspond to an entry in my hash table? Or might I get values from my hash function that do not correspond to entries in my hash table? How might that happen, Elijah?
However you decide to the same as you say you divide.
Whoa, where'd division come from? I'm confused.
I was just thinking about the different ways to undo switch to.
So let's not get ahead of ourselves too much yet. So I've got a total coming from here. Let's say n is 8, like what you have in front of you. If you imagine running this hash function on an arbitrary string, do you think the result is guaranteed to be between 0 and 8? Like, how much bigger than 8 do you think it could get if I've got 10 letters? Like a little bigger or a lot bigger? How much bigger, Graham?
Probably a bit.
Quite a bit bigger, yeah. So even if I had a really simple encoding where each letter was just a number from 0 to 25, say, and I've got 10 letters, and I add them up, what's the biggest value I would get? 250, right? If they're all Z's, right? Or whatever. And Unicode has a lot more choices than 25. So we're going to get a really big number, like 250, but we've only got 8 little squares to put it in. So what might we do then to take our 250 possible values and squeeze it into 8? So there's some kind of magical arithmetic operation that could somehow take our 250 and guarantee a value between 0 and 7. Some just amazing miracle of an arithmetic operation. The what? So the log is an interesting idea because certainly we've experienced that if we take the log of something, we tend to make the result fairly small. In fact, the log is basically telling you how many binary digits does it take to represent this thing. So the log will certainly compress it quite a lot. But it's really hard to make the log guarantee it's as small as 8. It makes it really likely, but it doesn't guarantee it. So that was a great guess and a great suggestion. But I'm saying there's an arithmetic operator out there that we saw back in Computer Science 150, used in all kinds of weird, unlikely places, that would absolutely guarantee this. Mod! Yeah. So, when one first encounters mod as an arithmetic operation in a programming language, tend to be looked at and be like, whatever, who cares about the remainder, right? Turns out everybody does. And the reason that we care about remainders so much is that what mod does is it can take integers on an arbitrary interval and transform them so if the domain is an arbitrary interval, the range is going to be restricted to between 0 and k if you apply mod k to that arbitrary value. Technically speaking, this doesn't really apply in a computer because every possible domain is finite in a computer. But mathematically speaking, modulo can map an infinite domain, like the integers, to a finite range. You can take the infinite and make it finite, and you can make it as finite as you need it to be. That's what makes mod like the most amazing arithmetic operator. Takes something unbounded and makes it bounded. So yeah, I can take my hash function and I can just, so in other words, I can call hash s and I can mod it by 8 and I now have an index. And this absolutely positively is guaranteed to work every time to create an index. So already, with what we've talked about today, we have all of the most essential ingredients for creating a hash table. Now, there are some other ingredients we're going to talk about as well, and hashing turns out to be an enormously subtle subject, and there are huge numbers of variations of hashing. But all the basic ideas are sitting literally right in front of you. Okay? We have an array, but our data doesn't happen to be integers. So what we do is we use a hash function to turn our data into an integer, and by doing so, enable it to become an array index. This idea is so important and so useful that every single class in Java has a method called hashcode. So that hashcode method always returns an int for whatever the data type happens to be. Always returns an int. And so for your data type, you can always think about what's a good hash function, and you encode it just right there along with the data type. Now, to be honest, I don't always want to think that deeply about every data type I create. So let me show you a fun little Java shortcut. If there's any chance that your data is going to be hashed, you can implement hash code very, very easily by returning toString .hashcode. So in other words, as long as you've got a way to define your object's appearance as a string, and to do this, by the way, you should also have overridden equals and given it a nice definition of equals. So as long as you've done that, you can immediately kick right on out a hash code, which is pretty convenient. So as we wrap up, I want to ask you all, can you imagine any disadvantages to this hash code?
There's a chance that you might have two strings that have the same value.
There is, and how might that happen? There will always be strings that share a value. That happens with any hash function because we're taking an array of ints and making a single int. So in that distillation process, we will have collisions. But what about this specific function might lead to collisions frequently? I'll give you all a hint in the form of a riddle. Let's say there's an ant peacefully walking outside of its anthill, and it's basking in the sun, and we'll use our imagination here. And the ant gets a tan. Let me spell it out. The ant gets a tan.
The same letters or in different order.
Right, these are anagrams, right? So any two strings that are anagrams are going to produce the same hash code. Now, as long as they're anagrams, this works great. Once you got an anagram, you got, or a palindrome, oh, no, not anagram, yeah, then you got a problem. If your ant needs to get a tan, and both the ant and the tan go in your hash table, you got a problem. So we're going to talk more about this on Monday. And obviously Tuesday's lab is going to be creating your own hash table. So why don't you put your cards into two stacks, one with the numbers and one with the animals, and I'll come around and gather those. And we will talk more about this